So let's look at some more examples of deterministic finite automata. Again, I'm just covering more and more examples so that you become comfortable with thinking in terms of mathematical models like finite automata. Okay, so the last one that we saw was how to construct a finite automata which will accept strings that start with AA or BB. Right now, this time we want to build a finite automata that accepts a language which consists of strings that end in AA or BB, not start. Okay, the keyword here is ending in AA or BB. So if you think about this language basically has XAA or XBB, right? Such that X belongs to sigma star. Obviously, by default, our sigma is A comma B, right? Unless stated otherwise, right? This is a basic assumption that we made earlier. Now if you think about this language, right? So this language would have AA also, because AA ends in AA, right? Similarly, it should accept BB also. Similarly, it should accept BAA also. It should accept ABB also, right? So on and so forth. Because we are saying it should end in AA. This is ending in AA, this is ending in BB, and so on and so forth. So how do we start designing an automata for this? Right? A finite state automata for this. So let's go. So we'll have Q0 here. Look at this. It has to accept AA and BB. So let's start doing AA and BB first. Okay, so if I do A, okay, AA. Okay, so this is your AA. Very good. This is your Q2. Very good. Now it should also accept BB. Okay, so let's actually do that. Again, we want to construct minimum finite automata whenever we can. So this is Q3, this is B, this is B, this is your Q4. Now one thought that I had was, why don't we combine Q2 and Q4 so that we reduce the number of, see, one possibility is I could have B and then B here, right? But that would introduce problems. I'll tell you why. Okay, so again, this automata requires 5 states. You cannot get away with 4 states. Again, we'll realize that as we progress through this example. Okay, I tried to construct this with just 4. Like for example, I could do B here and again connect this vertex and this vertex with the B, because that would accept AA and BB. But then we'll run into problems as we progress, right? So we needed the 5th vertex anyway. Okay, so now let's continue the exercise, right? It should also accept, so it accepts AA, it accepts BB right now, BAA. Okay, this is B. Okay, this is B. Now it should accept BAA also. Okay, how do you do that? So what if I do this? This is B. The first word, the first alphabet here is, the first character here is B. Now what if I do this? What if I make it go here? BAA. Right, now it's working out for BAA also. Very good. What about ABB? A. What if I make BB? ABB. It's also working for ABB. Look at this. So this is also working for this. Okay. Now let's look at more cases. Of course, this is not the end of it, because if you look at this, for this state, I have both transitions AB. For this state, I have transition A and transition B. Good. For this state, I have transition A and transition B. For this state and for this state, I don't have any more transitions. For example, look at this. Suppose if I have AAA, what should happen? Look at this. AAA. This should be part of this language, right? Because it ends in AA. So if I have AA and then again A, makes sense. Or even if I have AAA, right? So it makes sense now. Similarly, if I have BBB or BBBB, all of them should also be accepted. So I have BB here. So if I place B again here, but if I place B again, this is cool. This is working out. So for this vertex or for this state, A is done. For this state, B is done. For this state, where should B be? Where should B go? Look at this. Where should B go now? That's important, right? So what if I have AA, B? So let's see. AA. So A will bring me here. Now then if I have B, right? If I have B, where should I go now? Because I have already seen one B. Look at this. See, what is this state saying? This state is saying that I have already seen one A. Okay, so this state says I have already seen 1B. So what if I connect it like this? Look at this. If I connect it like this, then A, B, B will take me to the final state. Very good, right? Suppose if I have A, B, A, even that will work here. A, B, A. That's also working well. Perfect, right? So this is sounding good enough till now. So similarly, again, by symmetry, look at this. I also leverage symmetry here, because this path or this part here, this part is contributing to strings that end in AA. This part is contributing to strings that end in BB. Okay. So one part that is still missing here, one edge that is still missing here is for this state A. Where should this go? By symmetry, it should go here. Because now, if it goes here, we'll have BBAA. Yes, working well. Right. So for example, this should also accept BBAA. Yes. So you have BBAA. Now for every state, look at this. For every state, every transition is now taken care of. And we are also leveraging the symmetry property. Or we are leveraging symmetry to actually construct this very smartly. Okay. Because this part is primarily for strings ending in AA. This part of the graph or this part of the finite state automata is for strings that end in BB. And they should look more or less similar except for the symbols. Here you will see A's, here you will see B's. Okay, now all cases have been handled. So for this finite automata, you need at least 5 states. So the minimum finite automata itself needs 5 states. You cannot get away with trying to do it with just 4 states. Again, I strongly recommend you try that. Okay, so the next one. Okay, so let's continue on the same journey. Now we want to construct an automata that accepts strings that contain AB as a substring. So what does this mean? This means I'll have X, A, B, Y such that X, Y belongs to sigma star. Right? So this basically means I have something, AB, something. Right? So this is the string that I want to construct now. Now how do we do that? Now let's look at some examples of this, some example words in this language. Right? We'll have AB in this language, obviously. You need to have AB in this language. So for example, so let's start constructing for AB. So this is my Q0, this is my Q1, this is A, and then this is my B, right? So this is my Q2. Very good. Now, see, can we get away with just 3 states? I don't know. Let's try that. Right? So what if I have BAB? This should be part of this language, right? So you have AB, something before A, because AB is a substring of this. So then where should, see, BAB also should be accepted here. So let me try to not add any more states and try to see if I can solve this problem with just 3 states. So if I have B here, if I just make my B stay here itself. So what this state is saying here is I have seen enough number of B's. The moment I see an A, I jump here. Right? The moment I see an A, I jump here. Right? Now if I continue seeing A's, so for example, if I have A, B, this should also be accepted. Okay, this should also be accepted because it has AB as substring. So now the moment I see the first A, I jump here. Right? Now if I see A, if I continuously see A again, I should stay in the same state because AB will also be accepted now. Right? So what about AB followed by something? See, I've seen AB. I've already seen AB. Right? I've already seen AB. If I keep seeing B or A or anything after this, I'll continue to stay in the final state itself. Now, if you notice, I have all the transitions. From this state, I have transition on A, transition on B. For this state, transition on A, transition on B. For this state, transition on A, transition on B. That's it. Right? So all the cases you can think of, are handled. Again, I just need AB as a substring here. Right? So something, AB, something. Again, this something can be epsilon also. Could be an empty string, right? So that's it. You need the minimum DFA that you need here. It consists of just 3 states, right? So now we have seen substrings also. Look at this. Look at the way we are progressing. First, we looked at starting with something, then ending in something, then as substrings. Now, what if I want to have something more complicated as a substring? Okay, so suppose if I want to have AAAA as a substring, how do I construct this? Okay, so what is the language here? X AAAA Y, such that X comma Y belongs to sigma star. Right? So for example, AAAA is also part of this language, right? Because I have AAA as a substring of AAA. Because I need 4 A's, probably I will need something like this. Q0, this is, I've seen my first A, then I come to Q1, I've seen the second A, I come to Q2, I've seen the third A, I come to Q3, I've seen the fourth A, I come to the final state. Look at this, I have 4 A's as a substring. Okay, so now I have 5 states here, if you notice. Here I needed only two character substring. So I needed 3 states here. Okay, so let's keep going. Okay, so till now everything is looking good, but can I get away with 5 states? I don't know. Let's try that out. Okay, so what if I have B or B followed by AAA or some number of B's followed by this? Okay, all of them should be accepted. So which means my transition, if I have B, I'll just simply keep transitioning like this. Now what if I have A, B followed by AAAA? Look at this. For this state, A and B are taken care of. For this state, A is taken care of, but B transition is still not taken care of. So for example, so this will take me here. So A, B. So where should B go now? So that if I get 4 A's after B, again I'm working. Again, this word will be accepted by this machine. So A, again, if I get a B, the moment I get a B, I just go back here. Similarly, what about, so for this state, I have the transition on A, but transition on B is still not defined. So what if I get, see, AA will take me to this state, right? So AA will take me to this state. If I get a B now, where should I go back to? Again, if I get a B, I need to get 4 more A's for this word to be accepted. Which means when I get a B, I should just go back to the initial state itself. Similarly, same logic applies here also. If I get a B, I should just go to this state. Now, once I reach a final state, I've already seen AAA. Look at this. I've already seen AAA. Now, whatever else I see, it would consist of A's or B's. Whatever I see, it still has the substring AAA. That's it. That's all is the logic here. Look at this. With 5 states, we could construct a finite automata which accepts AAA, 4 A's as substring. Very simple example. Now, what if I want to have, again, I'm just complicating the examples here. Again, we are going step by step. First, we have seen all the cases with starting with AABB, right? Starting and ending in different symbols, starting and ending in same symbol, starting and ending in a single symbol. So from there we started, right? And we're constantly upgrading or constantly building complex examples. So 4 A's as substring. Now AA or BB as substring. How do we do this? Look at this. We have actually constructed this. Strings that end in AA or BB. This is ending in AA or BB. We have constructed this, right? Now what do we want? We want something where we want strings that contain AA or BB as substrings. Which means diagrammatically thinking about it, it looks somewhat like this. But not exactly this. Obviously, we'll have to change it slightly. But it looks very, very similar to this. Okay, so let's see. I want A or BB as substring, right? So my language will consist of XAY or XBBY, right? Such that X belongs to sigma star and Y belongs to sigma star. Okay, so this is what my language will look like. So language has to accept AABB, right? Language also has to accept AAA. Okay, we'll construct the basic diagram first for A and BB. Okay, again, we will try and keep the number of states as small as possible. A, right? So this accepts AA. So this is my state Q2. Similarly, let's also do BB. Okay, so this is my state Q3. Now this time I'll try to connect this. I don't know whether this will work or not. Okay, if it doesn't work, we'll create a new state. So this time I'm trying to finish off with just 4 states. If you look at a very similar example here. Here we said we needed 5 states because I actually tried it beforehand. Okay, so if I don't have the 5th state, things won't work here. Here I don't know. Here I haven't tried it. So let's actually go with the flow. Okay, if something fails, we'll anyway create a new state. But let's go step by step now. Okay, so this accepts A, this accepts BB. Now let's start this at this state. I'm at the very beginning, right? What if I get AAA? What should I do then? Look at this. Oh, I don't have to worry about it, because for this state, both transitions on A and B are defined. So this state is taken care of. Now for this state, okay, transition on A is taken care of, transition on B is not yet taken care of. Okay. So now when will I arrive at this state? For 1A, I'll arrive at this state, right? So 1A, I arrived at this state. Now if I keep getting A's, look at this, A followed by A, I will reach here. Okay. So A followed by B, where should I go now? A, where should I go with B? Suppose if I get A, B, B, I should go to the final state with A, B, B. So A, B, B. Look at this. So this makes sense now, right? Because A, B, B should be accepted. A, B, B. Now it's accepted. So for this state also, transition on A, transition on B is defined. Very good. Now let's look at this state. What should the transitions on A and B be? Look at this. I already have AA or BB as a substring by the time I reach here. Now whatever else I get, I don't care. So for example, AAA, AA. If I get an A, I should be here. Similarly, if I get AAB, AAB, I should stay in the final state itself, because AA is already a substring, right? So this part, so for this vertex also, both the transitions are taken care of. Now let's look at this vertex. This is the only vertex left, right? For this vertex, B transition is taken care of. But what about A transition? When will I reach this from the beginning? If I get B, I will reach here. If I get B, I'll reach here. Now if I get an A, where should I go? Okay, should I go back to Q0, Q1? I can't go here, because BA doesn't contain AA or BB as substring. So I can't go to the final state, obviously, right? But if I get BA followed by A, this should be accepted. B, if I write my A transition here, BAA should be accepted, right? So this is my final diagram, right? All the cases are handled now. All the cases are handled, and for every vertex or state in this graph, right, all the transitions are also handled. So I'm able to get away with just 4 states in this case. Unlike in the previous case, where we wanted the strings to end in A or BB, where we needed 2 of them. Look at this. Look at this. So you see these cross connections. You see these cross connections. We encountered the same cross connections here also. The same cross connections, right? So instead of having 2 end states here, we just have 1 end state. And once you reach the end state, you don't care about it, because here you want it to end in A or BB, right? That's why you have 2 distinct end states. In this case, once I observe AA or BB, I don't care what is there at the very end. At the very end, it could be anything. That's why I don't need the 5th state here. Okay, again, it's very important to compare these 2 diagrams so that you get an appreciation of why we needed 4 states here when we had substrings, when we had ending in A or BB, why we needed the 5th state. Okay, that appreciation will give you, that conceptual understanding will give you a much deeper appreciation of the finite automata concept. Okay, now let's look at one more example, slightly more complicated example. AAA or BBB as substring. Very easy. So this language will contain AAA. This language also will contain BBB. Again, let's try to extend this. This is AA ending in this. This is BB ending in this. Let's try to extend it slightly. Okay, again as substring, right? So what if I start here Q0, right? I have my A, Q1, A, Q2, A, Q3. So this accepts AAA. We wanted to accept Q4, B, Q5, B. Again, again, I don't want to create Q6, because for substrings, something like this worked out. This AA going to the final state, BB also going to the same final state, it worked out. So let's try to do it similar way. So this accepts AA, this accepts BBB. So these 2 are taken care of. Good. Now let's go to the slightly more complex case. Okay, for this vertex, everything is taken care of. Both transitions are taken care of. For this, if I get a B, where should I go? So I got A now. Look at this. I got A. If I get a B, where should I go? After this B, if I get 2 more Bs, right? If I get 2 more Bs, I have BBB as a substring, which means if I move here, look at this. Again, the lesson learned from this here is you'll have these cross connections. Okay, same lesson I'm trying to apply here. A, B, B, B. Very good, right? Similarly, what if I have AA? Look at this. What if I have AA? Okay, suppose let's assume I have AA. Then if I get a B now, where should I go to? Because I've seen 1B, I should just go here. Because this state says I've seen 1B. After that, if you see 2 more B's, you should go to the final state. Right? Very simple concept here. Okay. So now let's look at another example. From this state. Okay. So from this state, A is taken care of, B is taken care of. So this is good. From this state, A is taken care of, B is taken care of. Good. Now you need to have symmetry because this path is 3 A's, this path is 3 B's. Right? So now if you see again, so this path and this path will look symmetric because instead of A's, you have B's here. That's it. Right? So this A transition. So you have seen B. Now your A will go here. Right? Because B, A, A, A. You have seen 3 A's now. Perfect. Similarly, if you've seen 2 B's, look at this. 2 B's you have seen. Now if you see an A, you've seen 1 A, which means your connection should go here. Your connection should go there. Right? Now, which means for this vertex and this vertex also, both transitions on A and B are taken care of. The only thing left is this. Right? So once you have seen 3 A's or 3 B's, whatever else you see, you don't worry about it. Because you've already seen AAA or BBB as your substring. See how fast we can construct these finite automata once you get the basic concept clear. Okay, that's why I've like this is almost like example 17. Okay, the reason we are going through so many examples is because once you see enough examples, you can actually draw this in the middle of night also. If I just wake you up in the middle of night, you can quickly look at these, look at all the words and construct this in like no time. Okay, so this is example 17. Let's go for slightly more complex example, slightly more complex. You want odd occurrences of substring AB, odd occurrences. Okay, not even occurrences, but odd occurrences of AB. So for example, let's look at this language, right? So you have odd occurrences of AB, which means AB. Okay, odd. So odd basically means 1, 3 occurrences, 5 occurrences, 7 occurrences, 9 occurrences, and so on. Odd occurrences of substring AB. So AB will be here, right? AAB will be here. Very good. BAB also will be there because you have 1 occurrence of AB in all these 3 cases. Okay. Now, for example, something like AB, AB, AB will also be there because you have 3 occurrences of AB, AB, AB. Right? So, okay, these are some examples. Let's start constructing again. The odd part we have to be very careful of. This is slightly more complicated example now. Okay, first let's start with the simplest case. Okay, so you have A, Q1, you have B. Obviously, you have to accept this. This is your Q2. Very good. So you have 1 occurrence of AB. Okay. Now, if you have BAB or if you have BAB, see for this state, let's see if we can get away with 3 states, or else if you need 4 states, we'll add that as we need. Okay, so this accepts AB. Now this does, so for example, BAB. So if I have this transition B here, if I have this transition B here, look at this, if I have this transition B here, so this state is saying that I have not yet seen any A. At the very beginning, if I keep seeing B, 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 A, B. Okay, so it's basically maintaining the fact that I have not seen a single A till now. Okay, I've only seen B's. Okay, so this state is taken care of because both transitions A and B are taken care of. Now let's go to the next state. For this state, transition B is taken care of, transition A is not yet taken care of. Now what if I get A, B. So now I got multiple A's. Where should I be? I should continue to be in the same state. Because now I'm just seeing A's. The moment I see B, so this state basically means the last word, so the last symbol that I've seen is an A. Now the moment I see a B, yes, I'm seeing my first, again, this is all for just 1 occurrence. We have not yet gone to 3 occurrences. Okay. Now if I get, okay, so now I've got an A, B now. Okay, this is good. If I keep getting B's now, look at this. Again, let's solve the simplest case, which is just 1 occurrence of AB. Then we'll go to 3 occurrences, 5 occurrences, etc. Okay, so now what if I have AB followed by B, 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 B? What should that be? So AB, I've already reached here, right? If I keep getting B's, that's perfectly okay. There is no problem with it, right? Because I only have 1 AB now, odd number of AB till now still. So this is also good. So this vertex is taken care of. This vertex on transition A, where should I go now? Okay, for example, suppose I've seen an AB. I got another A. I got another A. Now where should this transition be? So one possibility is to transition here. One possibility is to transition here. Okay, that's one possibility because I've seen one AB. If I see another AB, yes, AB, AB. Very good. So this might be the correct one. Then we are very good, right? Because we are done with just three. We are simply done with three states. Is there some case where this might fail? Let's see. So what if I get AB? So I got AB. I've already got one AB. Now if I get AB, AB. Sorry, if I get AB, AB, something like this. 2 times AB, AB. Okay, because this should not be accepted. Okay, oh, actually this also should not. This is the same thing, right? So AB, AB should not be accepted because the number of occurrences of AB are even. AB is now being accepted, which means this cannot be there, right? Because even occurrences are actually working out here. Only odd occurrences of AB should be accepted. Even occurrences should not be accepted. But this automata is now accepting it. So you're now forced, because with just these three states, you cannot solve this problem, right? So we are forced to introduce a new state. So let me introduce a new state. Let's call it Q3. So what if I go to this state? What if? I don't know again. Okay. So I got AB, I go here. So for this state, so when I reach this state, what it means here is, till now I have seen odd number. So when I reach here, what does it mean? I've already seen odd number of occurrences of AB. Now the moment I see A again here, I reach here. Right? Now if B is here, okay, again, let's tackle this. If I see a B again, okay, so let's see. Suppose if I have AB, AB, okay, where should this, so AB, A, where should this B go to? This B cannot go to this. Okay, this B cannot go to this. Because if this B goes here, we are accepting odd number of ABs. So it cannot go here. What if it goes here? If this goes here, then AB, A, if this B, so if this B goes here, right? AB, A, B, B. AB, A, B, B. Sorry, AB, A, B, B. This will be accepted now. If this B goes here, so for example, let's actually write this, right? So if this B goes here, AB, A, B, B. This is accepted. But this has even number of ABs. So this cannot be true. So I cannot connect it to this. Right? So what if the only option left for me is to connect it to this vertex now. Okay, let me connect this on A. Okay, on B, if I connect it to this, what happens now? Let's see. Again, I don't know. I'm still experimenting here. So will this be accepted? No. Will AB, AB be accepted? AB, AB will not be accepted. Okay, it will not be accepted. Now, but will AB, AB, AB be accepted? Yes. AB, AB, AB is accepted. So this path, so when you are here, when you are in this state, it means that you have seen 0 ABs, or you have seen 2 ABs, or you have seen 4 ABs, or 6 ABs, or 8 ABs. Right? If you see even number of ABs, you will reach this state. Okay, look at this. When I have 0 ABs, I reach here. When I see 2 times AB, 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 you have reached here. If you see 4 times AB, 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 you reach here. So this state indicates that you have seen either 0 ABs, 2 ABs, 4 ABs, 6 ABs, or 8 ABs. Very good. Which means this state, because from here to reach here, you need one more AB. Which means this state will now tell you if you have reached 1 AB, 3 ABs, 5 ABs, 7 ABs, 9 ABs, so on and so forth. Very good. This is what we want. Is anything missing now? Look at this. For this state, both transitions A and B are here. Oh, for this state. Now, for this state, transition on B is here. But what about transition on A? So, for example, when would that happen? We have AB, A. And if I'm continuously seeing A's now, where should I be? I should continue to be in the same state. Because if I see a B now, then I'll go here. Because I've seen one AB and second AB. Okay. So for this state also, both the transitions on A and B are taken care of. See, we couldn't solve the problem with just 3 states. We needed the 4th state here. Because to keep track of odd and even. Okay. So to keep, again, this whole state was needed primarily to, whenever we see an even number of ABs, we wanted to put it back here. And for that, we needed AB path. That's why we had to introduce this vertex or this state. right? So very good example. So we need 4 states to solve this problem. It's a very good problem. This is a twist, but a very good twist. Okay. Now what if I want the even number of occurrences? So we have seen odd number of occurrences, right? What if I want even number of occurrences? It's going to be much easier now. See, look at this. This state, it's going to be the same diagram. If you think about it, it's going to be exactly the same diagram. Same diagram, but instead of odd number of ABs, if I want even number of ABs, I make my Q0 as my final state. It's going to be the same diagram with Q0 as my final state. Okay, let's actually draw that. Okay, so my Q0 will be my final state because I've seen 0 ABs. 0 is also an even number, right? So on B, I will transition here. I'm just copying this here. On A, I will transition here. And Q1, okay, AB, right? So AB, right? So this is Q2. On AB, this cannot be final state now because this tracks the fact, again, this tracks the fact that I have seen even number of ABs. This tracks the fact that I've seen odd number of ABs, right? So, okay, so I had this transition. Here I had this transition. Now I have Q3 also here. I'm just copying the same diagram here, okay? So what is this? This is A. This is again B. Now if I keep seeing A's, I will stay here. Everything else is done, right? So this. There are 4 self loops, all the paths are done. Yes. So this becomes, again, same diagram. It's exactly the same thing. Instead of Q2 being the final state, Q0 is the final state. Because this is tracking even number of AB occurrences as substrings. That's it. Very simple. Simple. Again, this question is a simple extension to the previous one. Right? So now let's go slightly more complicated. What if I want exactly 2 consecutive A's only? No more consecutive A's. So which means I want some number of B's here. Only 1 occurrence of consecutive A's. No more A's. This whole thing should be B. So we often write it as B star. So what does B star means? B star means epsilon, B, 2 B's, 3 B's, 4 B's, so on and so forth. Okay, similarly B star here. What does B star mean? I could have epsilon, I could have B, BB, triple B, any number of B's. Okay, again, this notation, this is for a character or this is for a symbol. So we also have sigma star, right? Which is basically set concatenation. Epsilon, power 1, sigma, sigma power 1, sigma power 2, sigma power 3, so on and so forth. This is your clean closure. Okay, it's a union of all of them. Okay, that's your clean closure here, right? What we have here is for a single symbol, B star basically means epsilon or multiple repetitions of B. Okay, that's what it means. So we can actually write this as B star AA B star. Again, this notation we'll again learn it when we learn about regular expressions. In the next chapter, we will learn about regular expressions where we'll re-encounter this. Okay, so what do I want? I want exactly 2 consecutive A's only, nothing else. Okay, so let's write down some examples of this language, right? AA obviously, BAA obviously, BBBAA, right? AA, BBBB. Okay, so on and so forth. Let's start constructing the automata for this. Okay, this is my Q0, obviously. My Q1, right? This is A. This is A. Okay, Q2. Very good. Till now, everything is looking good. A is now being accepted. Very good. Things are looking good. Now, BA. Suppose if I get BAA. Okay, I can just mark this B here. Good. So this state is taken care of. I'll try to see if I can solve this with 3 states. So on this state, A transition, what if I get a B transition now? So what will happen then? I got an A. Look at this. I got an A. Then I got a B now. Now, the moment I get AB followed by anything else, see, I want exactly 2 consecutive A's. If I get A or B or anything like that, this will never be part of my language. So if I get A, if I get B now, this has to be a dead state. This has to be a dead state. Sorry. This is B, my bad. Okay, so I should write this as Q3. Okay, because the moment I see A followed by a B, which means I've encountered an A without the consecutive A. Okay, and I want exactly 2 consecutive A's. I want AA, no more A's here, no more A's here. Right, that's very, very important for me. So the moment I see AB, whatever you come across later, this should be a dead state. I should never be able to come out of this state, right? So now for a dead state, what happens? All transitions will be to the same state. I'll never be able to reach this. Now, what if I get, so for this state also, transition on A, transition on B is taken care of. Okay. So now let's go to this state. If I get AA, right? Now after AA, if I get a B, look at this. After AA, if I get a B, this example, right? I can stay in the same state. It's always going to be a final state because I exactly have one occurrence of 2 consecutive A's and nothing else. But if I get 3 occurrences of A's, this should never be accepted by this language because I want exactly 2 consecutive A's, right? So I got 2 A's, which means the moment I get a third A, I should go to the dead state because AAA followed by anything should not be here, right? So I'm getting away with 4 states now. Again, I need a dead state because of these cases, because of cases like this, because of cases like this, I need a dead state. Very simple example. So I'm getting away with 4 states now. Very good example.